Hello, welcome to this lecture. We will continue discussing functions and graphs. In the previous lectures, we discussed simple functions like y is equal to x, x square, x cubed, and so on and so forth. And we also said that we can think of functions which are combinations of x, x square, and x cube. So that's where we said last time that we can have a function that is a combination of x, x square, and x cubed. And we also said that most of the experimental curves we get can be obtained by appropriately adding and subtracting these simple functions such as x, x square, x cube, etc. And one example we said is an exponential function, and it is y is equal to e power x. If we plot it by tabulating, we will get a curve that is increasing with respect to x. So this is also just like x, x square. All of these functions are increasing functions, like y increases with when x increases. And we said the way to write y as a function of x is an infinite series. So that is, you take many terms. So as shown in the computer here, e power x can be written as 1 plus x square divided by 2 plus x cube divided by 6 plus x power 4 divided by 24 plus x power 5 divided by 120 plus x power 6 divided by 6 factorial plus so on and so forth. So you can write this is a sum of many terms, and this 3 dots here indicates that you have to have many more terms, which I have not specified here, which we will get to know later. But e power x can be written as a sum of many terms, where each of this term is some x square, x cube, x power 4, etc. divided by some number. How this number is coming, etc., we will discuss later. But at the moment, it is sufficient to understand that an infinite series where we add all powers of x appropriately weighted by various numbers will give us e power x. One of the things that we want to note is that x is a dimensionless quantity. What do I mean by that? So when we learn math for biology, we should think of this not as simple just mathematical equations, but as some physical quantities. So when we say e power x, this x will be always some physical quantity. So sometime x will be some physical quantity, that is something that you can measure in experiments. But if you look at this expansion here, e power x is 1 plus x square divided by 2 plus dot dot dot. So you can see that 1 plus x. So one fundamental thing, physical rule is that when you add two quantities, here you are adding 1 and x, they should have same dimension. So x and 1 should have same. 1 is a number which has no dimension. Therefore x also should not have any dimension in this definition of e power x. So whenever we write x as a quantity, we have to write it as a dimensionless number. Only then that's what this implies. And we will see that x is indeed always written as a dimensionless number, and we will see that. Typically, for example, if t is x is some time divided by some another time. So if we can write some ratio of 2 times, x can be written as ratio of 2 times. So very often x will be written as t by t0, or sometime it will be written as t by tau. Tau, t0, they are all some time, some characteristic time, which we will understand. And some other time x will be some ratio of lengths. So L by L0 or L by lambda. All the lambda L0 are some kind of lengths. So when we write this as ratio, this will not of course have a dimension. Therefore, very often x, so you will also see some other times like it can be written as E by RT. RT has a dimension of energy, E also has a dimension of energy. So this essentially will not have a ratio of this, or it can be written as F by some F naught. This is some force, this is some other force. So ratio of some two quantities which are same dimension. Very often whenever you see e power something, the quantity in the power, e power x, that x will always be ratio of two quantities such that the x has no dimension. Always in biology you will see that, and therefore this also implies that e power x has 1 plus x square by 2 and so on and so forth, implies that x and 1, if you want to add x and 1, x shouldn't have any dimension, and indeed we will see that x does not have any dimension in all the cases that we would discuss. So this is something which you should keep in mind. I would urge you to look at the dimension of any equation that you see. So beyond mathematics, when we learn mathematics for biology, we should go slightly beyond mathematics in the sense that we should always think about the dimension of left hand side and right hand side. We'll train ourselves to do that, and first case is this, that x will not be having any dimension, and we will come discuss that. So now e power x, we said that e power x can be written as 1 plus x square by 2 plus x cube by 6 plus many terms. Let us now, what is this infinite series means and what are the implications of this? So there are 1, 2, 3, 4 terms here. 1 x square by divided by 2, x square divided by 6. There are 4 terms here. In that, if we plot only 2 terms, just 1 plus x only, what will we get? So if you plot y is equal to 1 plus x, we will get this red line. If you plot y is equal to e power x, we will get this green line. And when you compare this, so what we are doing here is we are comparing two functions. So what we said that y, which is e power x, and we said that this is equal to 1 plus x square by 2 plus x cube by 6 plus many more terms. That's what we said. Now, if we just take only 2 terms, so if we just take only first 2 terms, and if we just plot y is equal to 1 plus x, only these two take and neglect all other terms, what will we get? So we are going to compare y is equal to 1 plus x with y is equal to e power x, and that's what is shown here. Y is equal to 1 plus x is a straight line. It's just y is equal to mx plus 1, where m is 1, and therefore it's a straight line. And e power x is this green curve. What you can see is that very close to 0, so below 0.5, somewhere here, very close to 0, these two curves coincide. But for larger values, anything larger than 0.4 or 0.3, things start diverging, and then e power x and 1 plus x are very different. So what does this tell us? This tells us that when x is very, very small, when x is close to 0, e power x is approximately 1 plus x. So here, very close to x equal to 0, e power x is 1 plus x. So that's what is written here. When x is very close to 0, e power x is approximately 1 plus x. That's what this comparison tells us. Only when x is very small, e power x, all other cases this will not be true. Why do we get this correct? Why e power x is approximately 1 plus x when x is very small? Because when x is, let us say when x is 0.01, when x is 0.01, 1 plus 0.01, 1.01 plus 0.01 square, right? So if you look at here, if you take x is equal to 0.01, y is 1 plus 0.01 plus 0.01 square, which is very small number, divided by 2 plus 0.01 whole cubed divided by 6 and so on and so forth. So when you square this small number, it becomes smaller, and this is much smaller. So approximately this 1.01 plus one small number, so y will be approximately 1.01. So this is the reason that why this works. Why, when x is very close to 0, e power x is approximately 1 plus x. Now let us try another, let us take a few more terms. So in this infinite series, if we take 4 terms, if we take 1 plus x square by 2 and x cube by 6 and plot these 4 terms, that's what is this red curve here is. These 4 terms I have plotted. So I took an x value, calculated 1 plus x square by 2 plus x cube by 6 for different values of x and plotted it here. That is what the red curve is. Then I plotted e power x. What can you see? You see that it fits pretty well, even around 0.5, 0.6 somewhere, even here. For much larger values of x, where this is below 1, you can see that they match. But then again, it did start deviating for larger values of x. So these approximations will work for small values of x, and for large values of x, you would need to take more and more terms in this infinite series. So here is comparison. If you just take only 2 terms, so the green in both the left and right side, green is y is equal to e power x. In the red, left hand side, red is y is equal to 1 plus x. That is, I take only 2 terms, I will get this. If I take 4 terms, the red curve becomes closer to the green curve. If I take 5 terms, it will become closer. If I take 6 terms, it will become further closer. And if I take many terms, e power x will be equal to this sum of these terms. So what does this imply is that this tells us that as you add more and more terms, e power x is indeed sum of these powers, and one can demonstrate this just by plotting a graph. Okay, now we learned many functions. All of these functions are increasing with respect, when x is increasing, they are all increasing. All of this function increases with x. Now in nature, if you want to use mathematics as a language, you would also need functions that would decrease with respect to x, because we might want to describe a phenomena where things are decreasing with respect to x. So what are those some example functions where things will decrease? In some other cases, things will not be either decreasing or nor increasing, it will be oscillating. So these quantities so far represent, these functions represent quantities that are increasing with x. In nature, there are quantities, phenomena, where one should use equations to represent quantities that are decreasing or even oscillating. They could increase and decrease. So we'll discuss some example functions. First, some functions that would decrease, then some functions that would oscillate. And once we learn these functions, we can use them to describe some phenomena that we would see. So first function is e power minus x. So this is e power x we learned, e power minus x. So the expansion e power minus x can be written as 1 plus x square divided by 2 minus x cube divided by 6 plus many other terms. So again, this is also an infinite series. And when x is 0, so you put x equal to 0, this is 0, this is 0, this is 0. When x is 0, e power minus x is 1. So it starts with 1. So when x is 0, the value y value is 1. And then you put some x value, positive value, it will decrease. So this is a decreasing function. So as x increases, y will decrease. So when you can see that when x is 0, y is 1. When x became 2, the y already became 0.2 or close to 0.1. So it is decreased a lot when x increases up to 2. So this is a decreasing function. We can see that we said here that y for e power x, we wrote that y is equal to e power x, and e power x we wrote 1 plus x square divided by 2 plus x cube divided by 6 plus dot dot dot. Now instead of this x, here we substitute minus x. So here wherever there is an x, there we will put minus x. Then we would get 1 plus minus x plus minus x square by 2 plus minus x cubed by 6 dot dot. This will give you e power minus x. So e power minus x is the same expansion. Wherever x, you put minus x. So here e power x, this x you substitute minus x, you get the expansion for this. So this is what I want to describe here. E power minus x is nothing but 1 plus, instead of x we put minus x square by 2 minus x cubed by 6 plus dot dot dot. Same way we had written e power x, where wherever x you substitute minus x. Then if you expand this, you will realize that this is indeed this. And the thing you should remember is that this is a decreasing function and it decreases as x increases. Where are we would see e power x in biology? There are many examples where we would see e power x. Some of them is, we have heard this word exponential growth. We will learn about exponential growth, but this implies that the number of cells or number of bacteria or number of anything that is growing has this form, n is n0 e power t by t0. So with time this increases exponentially. So this is one example, and we will come back and discuss this. You can again here see there is t by t0, it's a dimensionless quantity. Rate of a reaction, you might have heard of this thing called Arrhenius equation. The rate of a particular reaction can be written as R0 exponential e power minus Ea by RT. So this is an e power minus x, where x is Ea by RT. So Ea is some energy, activation energy. RT is also some term which has the dimension of energy. You can it will have a unit in joules, and this is also in joules. So this Ea by RT is our x, which is dimensionless. Here t by t0 is our x. So this is e power x and this is e power minus x. So these are two examples where such functions will come, and as we go along we learn more and more examples. Now when it comes to e power x and e power minus x, things will become slightly complicated as we go along to plot it by making a table. There are many ways of plotting it. There are many software available to plot it. I urge you to go and look at internet and figure out some software, some standard software to plot. So how do we plot these graphs? You can use a scientific calculator, create a table and mark it on a graph sheet. This is the simplest thing that anybody can do. But you can use a computer to plot it. You can use a software. One free software is called GNU plot. So you can go to this website, or you can Google search for GNU plot and download GNU plot. It's a freely available software. It's a freeware. It's a open source software which anybody can download and use. Or you can use Microsoft Excel if that is available with you, which one will have to pay, I think. So you can use either of the software, and if you Google search, the Google search will give you some tutorials which will teach you how to use this software to make plots. So this software will help you to plot e power x, all functions, and I urge you to play around with this. One way to learn mathematics is to plot all functions. I urge you to play around with this software and plot all kinds of functions that we will discuss. So if you have a computer, do download either of the software and learn how to plot some functions, some equations using this either of the software, or you could use any other software you wish, MATLAB or various other free software available that would be available. But you should use whatever be the software, you should use it and learn how to plot some functions. We will have a short demonstration at some point on how to use some of this software. We will do that and put it up, that we will have the demonstration in one of the lectures. So this will help you to plot some functions. Now we will go to another kind of function that would be oscillating. So we had e power x increasing, e power minus x that is decreasing. What are the examples of functions that are oscillating? So there are many phenomena that is oscillating. For example, if you think of temperature over seasons, so you look at, we begin the lecture by saying that we would want to think of events around us as experiments. That is, so if you make a table of the average temperature of every month or every week around a year, you will see that we have summer, winter and all that. So the temperature will increase and decrease. So if you plot temperature as a function of time, seasons, you will surely see some interesting curves. So I urge you to do this. So all of you should plot. So if you plot here temperature in the y-axis and time in the x-axis in months, you see that at winter you will have a small temperature and then it will increase and then again decrease and so on and so forth. So you will see that temperature increases, then decreases, increases, decreases as the years go by. So this is not zero, this is some finite value. So in India, this would be like 10 degrees Celsius, or depending on the place, this value will be somewhere some small number depending on the place you live. In the up north, this could be 0 or even negative. So this is how the temperature might look like. So this is some guess plot. I urge you to take some data and plot temperature versus time and see how it looks like. So this temperature is one example where we will have things oscillating with time. Another example is biological clock. So as in a day, like we have day and night, you can even, as the day and night proceeds, we will have various proteins like insulin secretion, etc. will have some oscillatory pattern. In the cell cycle, we will have, as the cells divide, some proteins will have some activity which will also be increasing and decreasing. Now the question is, what is the mathematical function that we would use to represent this cyclic activity, increasing and decreasing activity? And one simple function is sine x. So sine is a function, it's a trigonometric function. So you have this function y is equal to sine x. How do we, if we plot this, so we want to familiarize with this. So it turns out the sine x can also be written as a combination of or various powers of x. So if you expand sine x, we will get x minus x power 3 divided by 6 plus x power 5 divided by 120 minus x power 7 divided by 5040 plus dot dot dot. So this is again an infinite series. You only have odd powers of x, x power 1, x power 3, x power 5, x power 7 and so on and so forth. And you can see that there is a minus and plus alternating. How is this expansion coming? I am not discussing that now. I will discuss that later. At this moment, I just want to tell you that sin x can be written as a combination of x, x power 3, x power 5, x power 7, x power 9, etc. And it turns out that this is the combination. How this is coming we will discuss later. If we plot this many terms and sum this and plot it, you will get this oscillatory function like this. So when x is 0, you can see that if 0 is, all terms will be 0. So when x is 0, the function is 0, and then it increases, it reaches a maximum value of 1, then it decreases a minimum value of minus 1, then it increases, reaches 0, then a maximum value of plus 1, then it decreases, so it oscillates between minus 1 and plus 1. So sin x is a function that would oscillate between minus 1 and plus 1. So if we have, so it would oscillate between, so this is plus 1, this is minus 1, and sin x will, and x is 0. So this is your x, and this is y is equal to sin x. And when x is 0, this is 0, and then at some point it will become 1, and at some point this will become 0 again, at some point it will become minus 1. Again, x, so let us say, typically as you know in trigonometric function, x is an angle. So x can be represented in radian. So when x is 0 radian or x is equal to pi radian, so when x is equal to pi radian, that is when x is equal to 3.14, pi, you know, pi is a number which is 3.14, it's an irrational number. So when x has that value, you will get some function. When x is pi by 2, when x is pi by 4, pi, 2 pi, and so on and so forth, you will have various values here. So one can take various values of x and plot this, and you will get this oscillatory function. So today we discussed e power x, how e power x can be approximated as 1 plus x square or 1 plus x for small values of x, and then we learned e power minus x, we learned sin x, which is an oscillatory function. So to summarize, we learned, so let me summarize for what we learned today. So summary, we learned y is equal to e power x, this expansion, and then we learned y is equal to e power minus x, then we learned y is equal to sin x, which is an oscillating function, and we will learn a few more functions in the next lecture, and with that we will stop the various functions and we will learn more things in the coming lectures. With this, I will stop today's class. See you in the next class. Bye.